Now we're going to learn one of the most important reactions for this section called the Aldol reaction. So this is going to be the addition of enolates to aldehydes and ketones. What we have shown here is an aldehyde, acetaldehyde, the 2-carbon aldehyde, reacting with itself to make 3-hydroxybutanol, and then also followed by the elimination of water to give 2-butanol to make this double bond. So we see that in both cases we have base present, so this will take place under basic conditions, though potentially you could also have these reactions take place under acidic conditions, and we'll see that soon. And also note that under acidic conditions, we have 2 different temperatures specified as well. We have one at low temperature and one at slightly elevated temperatures. So if you do these at low temperature, you can stop at the first intermediate, this initial aldol product, to give a hydroxy ketone. If you let it warm up, though, we're going to effect an elimination that takes place at slightly higher temperature to give a full aldol condensation. Condensation because now we're going to be making water along the way. So mechanistically, this is going to proceed in the same way we had before. Oh, I'll switch to a black pen, where the alpha hydrogen of this aldehyde is quite acidic, and we can have hydroxide make a small equilibrium with the enolate form. As we just learned, these enolates are reactive at carbon, and in solution we have an aldehyde that is also reactive, only now it's going to be electrophilic. So we have our good nucleophile that's negatively charged and quite reactive, paired with an electrophile. So since this reacts at carbon, we'll push the electrons down from the oxygen, and we're going to attack the carbon of the carbonyl because the carbon of the carbonyl is electrophilic. Along the way, we end up making a new alkoxide intermediate, where under basic conditions, we're always going to have negatively charged intermediates here. Where now water is around in solution, and it will regenerate our hydroxide. Oops. I can keep those electrons there and form the first product shown. So if you let this warm up, we still have more hydroxide around, and the new aldehyde we just drew still has acidic hydrogens. So hydroxide is able to still react with this newly formed aldehyde to effect a new deprotonation, and make a new enolate. So rather than do an intermolecular reaction with another molecule of aldehyde around, now it has another option. I apologize, this is not charged. This is still an alcohol. And so now we have a discrete negative charge on this enolate that's very basic, and it is able to do an intermolecular elimination of the hydroxide. So again, normally we don't want to have hydroxide as a leaving group, but in this case it's fairly efficient because it's an intramolecular reaction. This is similar in the same way that whenever we had hemiacetal equilibria, where we were able to eliminate a hydroxide from these tetrahedral intermediates because it was intramolecular. This is the exact same thing, only now we just have a double bond that connects the two. So these are still sort of connected through the frontier orbitals through the pi system, and it's able to directly eliminate this. So this is still a two-step process. So technically this is a variant of an E1 elimination. It's called an E1CB. So CB stands for conjugate base. So it is eliminating from the conjugate base of the aldehyde. And so again, this is not a concerted reaction. You don't deprotonate and eliminate all at once. It does go through an intermediate enolate that then eliminates the hydroxide. So as I mentioned, you can actually have the same aldol type condensation take place, only with acid. Here, it's a little bit more difficult to control the elimination because you're usually having a bit harsher conditions where it's more difficult to get these to stop at the first intermediate. So in this case, we're going to have acid catalysis. I'm just going to say H+. We're going to do the same protonation of the carbonyl to make this first acidic, this alpha hydrogen very acidic. Water will then act as the base to make our nucleophilic enol form. So now we have an okay nucleophile, and all of the ketones that are in solution, these are only okay electrophiles. So in order to get these two to react, we need to make this electrophile better. And we can do this through protonation since we're under acidic conditions. So in order for an enol to react with a carbonyl compound, it will need to be protonated first. And then we can still draw the same arrows. Enols are still nucleophilic at carbon. Note that we still have positively charged intermediates along the way. We start with a protonated carbonyl. Afterwards, we still have a protonated carbonyl, so everything's still positively charged. And then we can use water now as a base to take this hydrogen away. That gets us to our first intermediate hydroxy ketone intermediate. And now in order to make this alcohol into a good leaving group for elimination, we're going to need to protonate this as well. So first this will be protonated, and you can imagine this happening in two ways. So this will probably already start to ionize. You can imagine a hydrogen being deprotonated and eliminating this water group along the way to give the unsaturated ene-one product, the ketone that is next to a double bond. Alternatively, you could also imagine having additional keto-enol tautomerism take place where water leaves through just a slightly different form. I'm fine with either of these. It's difficult to know which one takes place. But this makes the process intramolecular, which might be a bit more favorable.